Oh, hey everybody, welcome back. Okay, we are about to take a look at what is called the integral zero theorem. Okay, the good old IZT. So first of all, once again, I have supplied an official mathematical definition. Okay, lots of words there. You can write this down. Okay, if you don't quite understand what's happening here, well, you're going to see with this example that the IZT itself, in its own as a theorem, the definition looks more complicated than the actual application. Okay, so again, this is not too difficult to do. But before we get to that, okay, I just have a few things on the right side of the page here that I want to go through with you. And again, okay, what we have here in the upper right corner is we have 4 different terms. They all mean the same thing. We haven't really looked at these words very much yet. But starting now, you're going to start seeing these words in different questions, and they all mean the same thing. So when we get into graphing next week, okay, you're going to see x-intercepts a lot. You might also see the word roots a lot as well. Okay, roots are also x-intercepts, and same thing with zeros, and same thing with solutions. So why do we have 4 words that mean the same thing? Well, that's a very good question. Okay, it's just like you could have money, but you could also have guap, you could have bands, you could have racks, you could have stacks, you could have cheese, you could have specific types of cheese like fettuccine, mozzarella, cheddar, feta. All these things mean money. So why do we have all these words that mean the same thing? Because we don't want to be boring. We don't want to say the same word all the time. And I guess that's what the mathematicians who invented math said, okay? They said, okay, we're going to have different words because we don't want to keep using the word roots all the time. That's fair. Okay, and then below that, all right, we see the difference between a factor and a root, or an x-intercept. Okay, x-intercepts and roots and solutions are just numbers. They're saying that x is equal to 3. That's an x-intercept. X is equal to -2. That's an x-intercept. The factors are the binomials that are in the brackets after you finish factoring. And you're familiar with that anyway because we spent some time and an assignment working on factoring, and you realize that your solutions come in smaller brackets with each of the binomials. Okay, so we're going to keep that in mind. The factors and roots are opposite of one another. That's not something that's immediately applicable, but it's definitely something that's going to come up over the next week or so. So you want to stay tuned for that. Okay, so what we have here, all right, is if you want to take a look at the IZT, the integral zero theorem, basically what we have is you have a constant term, which I've underlined here, -8. And what the IZT does is it's basically just a way of narrowing down your possible integral roots. Okay, so we have lots of roots that are whole numbers, that are possibilities, but rather going from an infinite number of roots, what the IZT does is it basically narrows down your possible roots to a smaller amount that is more manageable to deal with. So what we do is we say plus or minus, and we look at the constant term, which in this case is a -8. Okay, the negative doesn't really matter, okay, but the 8 does. So we look at the factors of 8, and we have 1, 2, 4, and 8. Those are all of the numbers that divide evenly into the number 8. So we use the positive and negative versions of that. So we've narrowed down our choices to 8 possibilities. Okay, so there's definitely 3 factors because it's a degree 3 function. What those degree 3 factors are, we don't know. But if we have to do any sort of trial and error methods, okay, basically what we're doing is we're going from an infinite number of possibilities. We're reducing that down. We're narrowing it down to, in this case, 8 different numbers. Positive 1, 2, 4, and 8, and negative 1, 2, 4, and 8. So those are your possible roots. This is part of a larger type of problem that we're going to work on. But for right now, okay, if you want to pause the video and just try out a few questions from page 133, number 4, all you're asked to do is get the possible roots. Narrow down your possibilities for when it comes time to do some trial and error. Okay, next up, we're actually going to apply the integral zero theorem along with the factor theorem and some synthetic division. So a lot of the little bits and pieces that we have learned up to this point, we're going to put together into one problem. Okay, so we're going to go through this one right now. This is a degree 3 polynomial, and we are asked to factor it. So we know in the big picture when we're finished, we're going to have 3 factors because it's a degree 3 function. And the 3 factors will give us 3 x-intercepts. What those x-intercepts are, what those factors are, we don't know yet. So there's a process to go through. So let's start with finding the possible roots using the integral zero theorem. I can take a look at the possible roots, narrow down my choices for a little trial and error method. I'm going to take a look at the factors of 3, which are only 1 and 3. So we have reduced the possible roots down to 4 possibilities: positive 1, positive 3, and negative 1, negative 3. Okay, so we have to do some trial and error. Okay, we're going to try x equals 1. We're going to try 1 at a time. And I would suggest to try with the smaller numbers like 1 or negative 1. So applying the remainder theorem or the factor theorem, I'm going to plug in positive 1, and I'm going to see, do I get a remainder of 0? If I get a remainder of 0, then that means that it divides evenly into that polynomial. So if I work this out, okay, you can do this in how many or how little steps you need. Okay, but what's going to work out here, what you're going to find out is that we end up with a negative 4 when you do all of the calculations, the order of operations. This does not equal 0, so this is not what we're looking for. X equals 1 does not work. It does not give us a remainder of 0. But that's fine. You usually don't get it on the first try. Let's try a second number of negative 1. So if I plug in a negative 1 for x, what's going to happen here? Am I going to get a remainder of 0? Let's take a look. So once again, okay, you want to do exponents first, then multiplication. So in this case right here, okay, I'm combining steps here. I'm probably working a little quicker than you guys, or maybe not. But yay, we get a 0. That's good news. So that means we have found one that works. So x equals negative 1 is an x-intercept. It's a root. But we're asked to get factors. And if I just click back here for a second, let's just remind ourselves on the right side of this is that if we have a root, x equals negative 2 in the case I have here, then the opposite, x plus 2, is the factor. So what we can say here, oh, sorry about this. Let's move ahead. So here we have x is equal to negative 1 is a root. Okay, so we can say x equals negative 1 is a root. Not really applicable for this question, but what is that x plus 1, the opposite, is a factor. So we know that we have 3 factors, and we have discovered what one of them is. Okay, we're not finished. We have to factor this in full. So we're going to move right along, and we've discovered that when we factor this down, we have one of the factors of x plus 1. Okay, what is the rest? What's remaining here? Okay, that is what synthetic division is for. So we are going to take this polynomial and divide by x plus 1, and we're going to see what we have left over. Now, we've practiced synthetic division before, so I won't go through the steps with you. Okay, that's in an earlier video if you need to see that. Okay, but what happens is, as is expected, we get a remainder of 0 because it does divide evenly. We already tried that, and we got a remainder of 0 using the remainder theorem. These numbers here give us what's left over. So now just moving on to this part right here, we have our factor of x plus 1, and using these coefficients that we found through synthetic division, we're left with 2x squared minus 7x plus 3. Now, to factor the quadratic that's left there, okay, there's a number in front of the squared term. This is going to require decomposition. Now, I'm not going to go through the process with you because you've learned that. You've done many decomposition questions. You can try that on your own as practice. Okay, you can try doing some decomposition. Or if you can factor it using any shortcuts, go right ahead. But you definitely don't need to use possible roots, remainder theorem, synthetic division when you get down to an x to the 2. You can use the factoring that you've already have learned. What I'm doing here is I'm shortcutting it. You're going to do decomposition. But here, okay, we end up with these factors right here when you complete decomposition on your own. and then we have this factored in full. We have our 3 factors for our degree 3 polynomial, and there it is. Okay, so next up, we have a second example. You can try this on your own. You can pause the video, try this on your own if you wish. I'm going to go through it right now. And we also have 4 more questions from the textbook that you can work on your own time, which are some more degree 3 polynomials. And this is going to be what you want to spend most of your time with. So for anyone out there who wants me to go through this in steps, okay, we're going to do our possible roots because we cannot factor this any other way. So I'm going to do plus or minus the factors of 30, and there are a lot of them. Okay, if you look at all these numbers, these are all numbers that divide evenly into the number 30. The good news is that we're not going to have to try most of them. Okay, when you start doing your trial and error, now that we've narrowed down our possibilities, start with +1 and -1, and they should get you the answers pretty quickly. If we try x equals 1, we plug in 1, this is not going to work. Maybe you don't have to write this out. Maybe you can look at this and just sub in 1. 1 is an easy number to square and cube, and perhaps you can get this without writing anything down. But most of you are going to see right here, all right, that this right here is going to give you a number that is not equal to 0. You don't even have to calculate what the remainder is. If you know it's not equal to 0, that's all that matters. It's actually equal to 16. Okay, but this will give us no. Okay, so we're going to try out x equals -1. If we plug in -1 for x, you're going to get the same thing. Okay, this is not going to work out. This is not going to give us a remainder of 0 that we're looking for. This is going to give us a remainder that is equal to 36. Again, if you know it's not 0, that's all you need to do. Okay, so we've tried 2 numbers already. We're probably going to get it on the next number because they're all designed to work out so that 1s or 2s will give you one of the roots. So if I try x equals +2 next, okay, I get 2 to the 3 minus 4 times 2 squared minus 11 times 2 plus 30. And then, of course, I may be skipping steps that you might want to include. That's up to you. But when I work through this here, I'm going to get an answer of 0 for my remainder. A remainder of 0, according to the factor theorem, tells us that we have discovered a factor. We know that x equals 2 is a root. So therefore, x minus 2 is the factor. We have discovered one of the factors of this polynomial. So next up, okay, now that we have x minus 2 as a factor, we can move right along here, and we had to figure out what quadratic function, degree 2 function, do we have left. That's where synthetic division comes into play. So let's hook up some synthetic division. It's already in descending order, so we can work our way through this. And again, okay, I'm going through this quickly because this is old news. But again, if you want to pause the video and do it yourself, and you may be a bit slower, that's fine. But we get a 0 remainder as expected because it is a factor, and these coefficients give us what's left over. So we're going to move on down here. We have our factor of x minus 2 that we previously found. We're left with a quadratic according to synthetic division. We get this right here. And then I can use simple trinomial this time. I don't even have to use decomposition. I can use simple trinomial factoring to factor that down further. 2 numbers that add to give minus 2, multiply to give minus 15, are minus 5 and positive 3. And now we have factored this completely. All right, so that's it. Okay, so once again, okay, once you take a look at those examples, I want you guys to work on, there's 4 more degree 3 factoring questions to do here. And next up, another day, we'll take it to the next level and look at degree 4 and degree 5 functions.